Okay, so let's take a look at the data which address our first question, which relates to how the calculation of step average ratio of forces affects that ratio of forces horizontal velocity profile that we're probably all quite familiar with from a lot of JB and Pierre's work to date. So what we've got here, one of the figures from the paper, is the ratio of forces horizontal velocity profile for one particular sprint out of blocks. And this is the same trial, but with step average ratio of forces calculated in two different ways. So the orange data that you can see on the screen here is the ratio of forces calculated from step average force data. So we calculate the step averaged vertical component of the force, the step averaged horizontal component of the force, and we use those step average force values to determine the step average ratio of forces. For the green data, what we did is calculate the instantaneous ratio of forces from the instantaneous 1000 Hertz force data, and then calculate the average of those instantaneous ratio of forces over the whole step. And you can clearly see, particularly if you look at the values on the slide there, we get quite different ratio of forces, horizontal velocity profiles, depending on the calculation method you use. Now, this is just one trial out of starting blocks, but if we look at all trials for the 24 participants that we had, we can see that clearly this was a consistent effect across all of our participants. And actually, this is for the RF0 value, so where it crosses the y-intercept. For all trials, for all participants, that was always higher for the step average forces method than it was for the average of the instantaneous RF method. So a systematic or mean systematic effect of about 8 or 9% you can see here. But importantly, there's quite wide limits of agreement around this. So it's not just a case that we can apply a fixed systematic offset, because different individuals do clearly have quite a range of different magnitudes of difference between these two calculation methods. And then the same goes for the DRF value as well. So again, clearly you can see that in all of our trials, it was clear that it was always a steeper gradient, so a more negative value for the step average forces method than it was for the average of the instantaneous ratio of forces method. So what does this mean? Well, essentially, we need to be very careful with how we calculate the data, and we need, as researchers, probably to report quite clearly the methods we've taken. For these types of RFV relationships, we think that the step average forces method is probably the more appropriate one, because it gets towards values at the late acceleration phase towards maximum velocity, which are more like the reality of values closer to zero. And actually, we think the instantaneous ratio of forces values get quite affected by some quite extreme RF values later in stance, when the actual magnitude of the force is being produced is very low and relatively kind of functionally ineffective. One thing perhaps to consider is when we use the step average forces, it's essentially more of a ratio of impulses produced during the step than it is a ratio of forces. And that's something we discuss in the paper.